I'm going to look at two related rates problems here. The first is a very typical traditional calculus question where the situation is we have a 13-foot long ladder leaning against a wall. The bottom of the ladder is being pulled away from the wall at 3 feet per second. And the question is, how fast is the top going to slide down the wall when it is 12 feet above the ground? So first thing I want to do is get all of the information out of the paragraph and then bulleted a little list of information in math language. So I first see that we have a 13-foot ladder. So maybe I'll say that the ladder is 13 feet, and that is a direct measure. That's not a rate of change. The bottom of the ladder is pulled away from the wall at 3 feet per second. So 3 feet per second, that is a rate of change. I am pulling the ladder this way at 3 feet per second. And so that is going to be the rate of change of something, d something, and I'll put a question mark for now, dt is 3 feet per second. We'll come back and figure out what exactly is changing at 3 feet per second. And the question is, how fast is the top of the ladder sliding down the wall? So if I'm pulling the bottom away from the wall, the top must be moving down the wall. And that is the question. We want to find how fast that is changing. And if the ladder is moving down the wall, the dimension that will be changing is the height of this triangle. So I have a height, and we're trying to find the rate of change of h, so dh dt. Find dh dt when the top of the ladder is 12 feet above the ground. So there's another direct measurement. The top, so we're looking at a point in time when the height is 12, and that is a direct measurement. And you should always, every time you are given a direct measurement, always consider if that thing is changing or if this dimension is always 12. So my height's not always going to be 12 because the top is sliding down the wall. So I'm going to put that in a little flashbulb that reminds me that that is changing. And let's go back up and talk about the ladder, because I kind of glossed over this a minute ago. The ladder is 13 feet long. The ladder is not going to change length as it slides. So 13 is always the length of a ladder. And if you have any dimension that is always the same, then go ahead and stick that dimension in the figure. We don't need a variable for the ladder length. That is a constant 13. The height is changing. And now we need to talk about this thing that is changing at 3 feet per second. That is a horizontal change. That is a horizontal rate of change. And so the horizontal dimension, the base of this triangle, is what will be changing at 3 feet per second. So dB dt is 3 feet per second. We're looking for dh. We're given the length of the ladder. The height at some instant is 12 feet. And that is everything I need out of the paragraph. The next thing I have to do is decide what formula to use to answer this question. So it is a right triangle. We could find the area, but the area is not going to help. There's nothing mentioned in this problem about the space under the ladder. We're going to use the Pythagorean theorem because all of the information given and the requested information is dealing with the side lengths of that triangle. So b squared plus h squared is 13 squared. And there is my formula. And now we will find the derivative of that. So there's our derivative. Do remember that 13 is a constant. Don't say the derivative of 13 squared is 2 times 13. That would be 0. And do remember your implicit differentiation. In the case of a Pythagorean theorem, you could simplify this a little bit and make it a little easier to work with by dividing everything by 2. And if you do that, you will simplify it to 2 dB dt plus h, to b dB dt plus h dH dt equals 0. So that'll make the numbers just a little bit smaller. And now I start plugging in everything I know. And so we will run into a bit of a problem, not a huge problem, but a bit of a problem. And that is that we don't know what the base is. We don't have a measurement for b. We do know that dB is 3. So I can plug 3 in for dB. I do know that the height is 12. We are looking for dH dt, so that will remain unknown. And now we have a situation where we have to solve for something in order to solve for b in order to finish solving for dH dt. So we have a side problem. I now need to find b at this instant. And usually, there will be exceptions, but usually if you find yourself missing a variable, a constant or something to plug in, you go back to your original equation, b squared plus h squared equals 13 squared, and we use that equation to solve for b in this instant. And if you plugged in 12 for h, you may recognize this as a nice clean Pythagorean triple, and b will end up being 5. So very frequently you aren't explicitly given all of the information, and this is one of those cases. And so I plug in my 5 for b, and now we should be able to solve this fairly easily. dH dt would be negative 15 over 12. If you want to simplify that, negative 5 over 4. And then for dimensions, for the units of measure, we did measure height over time. The height of this triangle would be measured in feet, and my time is measured in seconds. And there is your answer for this problem. Let's look at one more. And this one, we have sand falling from a chute at 20 feet cubed per minute. It's going to form a cone. The radius of the cone is always twice the height. At what rate is the height of the cone increasing the instant the height is 12? And then you are given the formula for the volume of a cone, so that's kind of nice. So let's look at this first line up here, and I see 20 feet cubed per minute. You can tell by the units that that is the rate of change of something, but in the question, they don't explicitly say the radius is increasing, the height is increasing, the volume is increasing. They don't tell you explicitly what it is, so you need to look at the units and realize that feet cubed is a unit of volume. Feet cubed is a unit of volume, so this would be the rate of change of the volume with respect to time. So dV dt is 20. The radius is always twice the height. That's a good piece of information. Radius is twice the height. I'm going to write that down. Radius is twice the height. At what rate? Here's the question. At what rate is the height increasing? So we are trying to find the rate of change of the height, dH dt. At the instant the height is 2 feet. So here we are given a direct measurement. The height is 2 feet, and the height is changing. We are not going to be able to plug in that 2 yet. The height is 2. However, that is instantaneous. That is not constant. So hold off on that. And then we have the volume. Now, for this problem, what you may be tempted to do is to look at the volume and find the derivative, which I did right here. There is your derivative of volume, and it would be a product rule. R squared would be the derivative is 2r dr dt. Leave the h alone, plus r squared dH dt. The problem you will run into is when you start substituting your values, you will notice that we are missing a lot of information. We're trying to find dH dt, so dH dt will be unknown. However, we need to plug in for r and dr dt. R would be pretty easy because we know the radius is twice the height, so if I have the height, radius would be easy to find. dr dt is a problem. We have too many unknowns, and so rather than work with this equation, I'm going to make a change because the product rule ended up being ugly, too many unknowns, and I'm going to take advantage of the fact that we know the radius is always twice the height. The radius is always twice the height, and if you are given a measurement or a relationship like that, and it is always true, then you can substitute that before you take the derivative. So we can make one of two changes. We could plug in 2h for all of the r's and turn my volume formula into 1/3 pi 2h squared h, or I could solve for h and plug in half r for the h, and both of these are usable. Pi r squared times 1/2 r. The way we decide which one to use depends on what we are given and it depends on what we're asking for. The problem is looking for dH dt, so you want to keep h's in your volume formula. So while 1/3 pi r squared times half r could be used, I want to use this one with all the h's because I'm looking for dH dt. So I don't need this. I'm going to substitute 2h for my r. And then before I do the derivative, I'm going to clean that up, and my volume turns into 1/3 pi 2h squared would be 4h squared. That'll simplify to 4/3 pi h cubed. And now my derivative just got significantly easier. I don't have a product rule. I have a nice power rule. The derivative of that would be 4/3 pi 3h squared, and I'm going to cancel those threes. So my derivative ends up being 4 pi h squared dh dt. And this just got really nice because now I don't have as much to plug into. dv dt is 20. 4 pi h is 2 squared. We are solving for dh dt, and that will end up being 20/16 pi. So dh dt is 20/16 pi, or if you want to reduce that, 5/4 pi. Height would be measured in feet, time is measured in seconds, and there is your problem. There's your solution. So I wanted to point out that if you are ever given a relationship that is always true, take advantage of that before you differentiate to knock out some of the variables and simplify the differentiation and the solving in the end.